All right, so here we're going to take a look. We're going to run through an example from the textbook. So the textbook calls this the crazy vector space. So example CVS. All right, so the crazy vector space. Okay, so we propose that the set C is the set of ordered pairs, right? X1, X2, such that again, X1, X2 are real numbers. Okay, and then C is a, excuse me, a subset of the Euclidean R2 space. All right, and we're gonna define the addition between two vectors in this set, or I guess ordered pairs, plus y1 plus y2 equals to x1 y1 and x2 y plus y2 plus 1, and then we'll define scalar multiplication as the quantity. So we have some alpha x1 x2. All right, then the operation performed here is alpha x1 plus alpha minus 1, and then alpha x2 plus alpha minus 1. Okay, so again, you might look at this and be like, well, this does not make any sense, right? How is this addition? How is this scalar multiplication, right? Again, but it is up to us because we define it this way, right? Remember, the definition of a vector space is given a set V along with two operations of scalar addition, as long as you define the two operations of vector addition and scalar multiplication, which you did here, right? And if all of the axioms hold, then it's a vector space, right? So, and all of the axioms do hold, right? Let's prove a couple of these, right? So we could see here. So again, U be x1, x2, V be y1, y2. And if we define U plus V, right? So that's x1, x2 plus y1, y2. And again, by our definition up here, this is x1 plus y1 plus 1, x2 plus y2 plus 1. Right, excuse me, this should be 1 right here. Okay, and then now again, these are real numbers, so we can just write this as y1 plus x1 plus 1, y2 plus x2 plus 1, and then this is y1, y2 plus x1, x2. So it's u plus v. Nope, it's v plus u. So it is the the commutative property holds. Okay, and then we can also take a look at this property here, right? The associativity of the scalar multiplication. So here, if we have alpha beta u, or alpha times beta, the ordered pair x1, x2. All right, and now the way we define scalar multiplication, beta, again, it's binary, so it's beta times the ordered pair here. That gives me beta x1 plus beta minus 1. And here, beta x2 minus beta minus 1. Okay. And then from here, again, we apply the rule again here of scalar multiplication. All right, so now we could treat this all as x1 and that as x2. So in doing that, we'll have alpha beta x1 plus beta minus 1 plus alpha minus 1. And here, alpha beta x2 minus beta minus 1. Okay, so it would look something like this. All right. All right, and then we simplify here. We get alpha beta x1 plus alpha beta minus alpha plus alpha minus 1, and alpha beta x2 minus alpha beta minus alpha minus 1, excuse me, plus alpha minus 1. All right, and then we see these cancel out here, and we get alpha beta x1 plus alpha beta minus 1, and then alpha beta x2 minus alpha beta minus 1. All right, and what this becomes is quantity alpha beta x1, x2, or alpha beta times my vector u. Okay, so we see that it is associative, right? Now, I want to go over a couple properties. I won't go through all 10, right? Because that is time intensive here. But one important property here is the zero vector property. All right, now it's not 0, 0, right? Because if we think of x1, x2, x1, x2, 0, 0, right? What is that equal to? Well, that would be the way we define the addition. We got x1 plus 0 minus 1, x2 plus 0 minus 1. So we get x1 minus 1, x2 minus 1. So we do not get back x1, right? So very much this does not equal to x1, x2. All right, now do we say this is not a vector space because this is not the zero vector? But again, that's not what the theorem states, right? It doesn't say that, or excuse me, our axiom states. It says that there is a zero vector that has the property where when you add it to a vector, you get back that same vector here. Now, this doesn't work with our choice of what we naturally think the natural zero vector to be, right? But what if instead of thinking of 0, 0, what if I instead chose the vector minus 1, minus 1? Okay. Or, excuse me here. Yes, plus, sorry. I got these switched around over here. So here, this one is fine for the scalar multiplication. Here, that's plus 1. Okay. Okay, so what if instead of 0, 0, I add the vector -1, -1? And what does that do for me here? So what we have here is x1 minus 1 plus 1, x2 minus 1 plus 1, and that gives me x1, x2. Okay, so we do have a zero vector that has the property that when you add it, you get back x1, x2. It's just not what we naturally think of a zero vector to look like, right? Our zero vector here looks like this, okay? All right, now the same thing here for the additive inverse, right? If we have x1, x2, the additive inverse is going to be defined as negative x1 minus 2 and negative x2 minus 2. All right, and we can see here when we do add these, right, x1, x2 plus negative x1 minus 2, negative x2, excuse me, negative x2 minus 2. All right, so that becomes, right, applying the addition rule that we defined up above, right, it's x1 plus here plus 1, and then x2 minus x2 minus 2 plus 1. Okay, and here, if we get this, we get negative 1, which, as we've established before, is the zero vector. Okay, so here again, just some surprising results that we get, right? What you want to understand here from this example here is that a vector space is defined entirely by its axioms. Any operations that satisfy those 10 properties qualifies, right? That works, no matter how unusual this may look.